Okay, I guess we'll go ahead and get started. Good to see you all again. And this morning we're starting a series of 3 talks that will be led by Dr. David Redden. Dr. Redden is the Vice Chair of the Department of Biostatistics. Actually, this is statistics. Sorry.
Biostatistics. It is biostatistics.
It is biostatistics in the School of Public Health. He got his PhD degree at the University of Alabama in 1995 in applied statistics. He's been active in the faculty at U of B for more than
23 years now.
23 years, and is really a tremendous resource across the campus. He's the director of the BIRD unit, which is through the CCTS, which he'll describe in some detail so you'll know how to access its offerings, and it's a tremendous resource that you should be taking advantage of. He's a member of the executive committee of the CCTS and is extremely interested in trying to give young investigators a clear foundation of the principles of statistics so that you'll be able to understand and have a good dialogue with a biostatistician as your work develops. And I think one of the main things we really try to emphasize here is that establishing that kind of relationship is an incredibly valuable thing for your own career development and for you to help conceptualize your research as you develop the ideas that you're most passionate about. The worst thing to do is to have this fantastic idea, design a big experiment, and then turn out that you've left out critical information that allows you to get nothing out of the data that you've gathered. And if you work with a well-matched biostatistician and with an informaticist, sometimes that'll really help you to make sure that what you do is the most effective work you can possibly do. So I'm going to turn it over to David, and Jean and I are going to be handing off the duties for the microphone. Please try to if you have something more than 3 or 4 words to say as a question, please raise your hand so that you can share what you're saying with the people who are joining us online. There are about over a dozen people who are listening in, so please give them that courtesy.
Okay. I can pass it, or either way. I'm the type of guy that I'll just be ready. I'm going to throw it. So we get ready to catch. So, again, believe it or not, I'm about to try to give you a full semester of biostatistics in 2 hours. But don't fear, because I'm not going to get into the formulas. One of the key things that we emphasize in our graduate program and even in the undergraduate honors class that we teach in biostatistics is, first and foremost, to get it right, you've got to understand the underlying concepts. I've often joked I was terribly scarred because my very first statistics course, I was exposed to it in a math department, and it was a bunch of formulas. Do this, do that, plug and chug, move your way through it without the conceptualization of, well, wait a minute, what's going on in the background? So what I'm going to do today is just to back up. Let's clear the foundation. Let's bring the structure down. Even if you have you understand it completely, it's always good to go back and talk to yourself about the fundamentals and how those basic fundamentals can keep you from getting yourself into confusion or a trap or overstating what you're finding with regard to your designs. So this is going to be ground level, assuming that, pardon me, it may sound arrogant, you were taught wrong. I'm just going to assume that, okay? The other thing, and I'm going to tell you that one of those quotes that I have always believed in, I think sometimes we have lost this in the past decade. The father of statistics, or modern statistics, is a gentleman by the name of R.A. Fisher. He was actually a geneticist. Almost all the material or the methods that we have came from competing groups. I'm explain that to you today because it's important that you understand why statistics is confusing. It's all our fault, not yours. But R.A. Fisher made a very bold statement at the end of his career. He said that to bring an experiment to a statistician after the experiment is over is to request the post-mortem examination. The methodologist will tell you exactly what your experiment died of. And my comment to that is that's extremely harsh, but my best, if you have, if there's one message I can give you at the end that you will walk away with today, at the beginning, at the very beginning, when you're starting to write your goals, your aims, reach out to a methodologist. I'm not saying you've got to find a statistician. I'm saying find a methodologist, find an epidemiologist, find a biostatistician, find someone to talk to about the fundamentals. Iron sharpens iron, okay? Keep that in mind. Don't be afraid. They're just going to ask you some fundamental questions that you need to discuss. Like, how many groups? What's your outcome? And then we'll navigate through that. And then we'll get to the idea of, well, how big of a sample size do you need? But today we just want to get the vocabulary down and the concepts down. That's all. So I'm going to give you, throughout this, a brief overview of statistics, the way I think about statistics. Also, what is statistical inference? When I teach any class introductory, I completely throw out the textbook because every textbook I've ever observed in statistics starts with, here's the formulas, which telegraphs the wrong message. It's not about formulas. It's about measurement. It's about probability. That's why I always say probability will come first. Probability should be the first chapter of every stats book. It's not. It's usually chapter 4. Don't understand. Talking about probability distributions, why you do not have to be an expert in probability theory or probability distributions, but you have to recognize when a statistician is asking those types of questions, or a methodologist, tell me your outcome. Tell me how many groups. What we're trying to do is we're trying to conceptualize in our mind what type of probability distribution can I match to this data. And by doing that, after I make that decision, that's when we can start discussing power. When we can start discussing how do we write the analysis plan? Because in every application, I am very serious about this. We must, before the experiments start, at least write down even just a fundamental outline of this is how the data is going to be analyzed, so that we do not get the classic paralysis by analysis, that we're trying so many different things that we are stuck. We've got to have a predefined strategy. The key thing, the secret of statistics is simply this. Every calculation, when I summarize your data, those statistics follow a probability distribution. Okay, I can tell you, if we condition on a belief, if we believe the null hypothesis is true, should you have seen that statistic, yes or no? Okay, I'm going to explain that idea of conditioning on the null hypothesis because it's crucial. Then we're going to have to talk about the central limit theorem. The key terms correctly defined, that's the biggest thing. There's a lot of discussion these days about rigor and reproducibility. And please understand, I'll get through most of this. Probably will not, I'm going to have to rush on the correlation and the regression. And then if we're going to talk about the history of statistical inference, why it's so confusing, okay? When you do a textbook, or when you go into textbooks, you see p-values. And then when we go to talk about, hey, let's calculate our statistical power, the p-value doesn't appear. Why? Why? What's going on there? There's a reason for that. Walk you through a couple of examples. Then we'll talk about statistical power because most people stop me on the street. I'm not joking. I'll be walking down the street. People will stop and say, how many samples do I need to I don't have that off the top of my head. Thank you. Could we come to the bird clinic on Monday from 10 to 2 on the 4th floor of Lister Hill, and I will have the software, and we'll walk through how many, what are you measuring, how many groups, and then we can get there, okay? Because we have to have the aims first. Then we'll talk about the correlation and regression. Every textbook out there starts this way. It talks to you about summarizing descriptive statistics. You start seeing the sample variance formulas. You start seeing correlation formulas. You see all these formulas. And then they jump into the laws of probability. Then probability distributions. Then we get into hypothesis testing. It's confusing. Nobody talks about why these things are synergized. How do they interrelate? I mean, the first time I went through a stats course, I thought I was taking 3 different courses. I really did. I did not see the rhyme or reason of any of this. Didn't make any sense to me. It seemed to be 3 distinct topics. And then, so when I started teaching, I kept emphasizing my class, the structure of the class is this. It's broken into thirds. First, we come to probability, and you understand that if we're talking about any type of event, any event, if I can put the right model to it, I can tell you what should happen. Weather forecasting, if I can get the right model, I should be able to predict. If I've studied enough about serum cholesterols and I understand what's the probability, I should be able to tell you with a reasonable chance whether Dr. Chaplin's on a statin. And if he's not, what's the probability that his total cholesterol level is above 225 today? I should be able to do that. Those are characteristics. But guess what? Your experiment generates a characteristic too. It generates statistics. And I just told you, statistics follow probability distributions. And we've got to be able to say, which statistics are we going to summarize? And what probability distributions do they follow? So we get into a teacher. Instead of seeing it as all these different topics, probability, statistics follow probability, and because statistics follow probability distributions, I can tell you whether the results of your experiment are extreme or not given your previous hypotheses. That's all it is. I know it sounds simple, but that's my whole career right there in 3 steps. Okay? All right? You got to remember, and I will say this. We're going to get there. Please keep in mind the p-value is not the sole measure of scientific evidence. Please understand that often everybody comes to me and they get so engrossed in p-values. And I'll be very honest with you. I will tell you, I do not believe that if I did a pop quiz on this campus today and said 1 question, define the p-value, write it, I do not believe that 25% of the people could get it right. And I'm talking about the 25% of the researchers could get what that is actually measured. What I want today is for you never to forget what it's really measuring, so you don't interpret it the wrong way, okay? When I retire, because I will never be able to write a textbook until after I retire, I'm going to write a probability first and talk to you very clearly about probability is key. We need to be able to predict, and the statisticians use a key word over and over. We talk about what we expect. And you'll see it all over the textbooks. Well, the reason we can say what we expect is because we are making or judging our expectations by the laws of probability. That's all. Better hope to get the distribution, but we do that. And then what we do is we say, well, we know that we can take a correlation that you measure, and we can tie that under certain assumptions back to a normal distribution. And then under that assumption, I can tell you, should you have seen a Pearson correlation of 0.25, if in fact there is no correlation between the 2 measurements, I can tell you that. Always remember, you need to hear me say those words, if, given. We're going to clarify those throughout this. Okay? All right? So, this is the way David thinks about the world. And nobody calls me Dr. Redden. Nobody stops me on the street. I'll tell you this much. If you see somebody come up to me and say, hey, Dr. Redden, then you know they're a student. They come up to me and say, hey, David. Then they know that that's a researcher, collaborator, colleague. Okay? But I don't, the doctor is a scary, to be honest with you, the only time I ever introduce myself as doctor is when I'm at a restaurant and I really want a good table. That's the only time I use the term doctor. Okay? Probability distribution is the way I think about everything. You come, when I look at this room, first thing I see is a binomial distribution. I've got males and females. I see another distribution. I see ethnicity. And the bottom line, all of these characteristics, everything to me is a probability distribution. You can laugh at me. When I go buy a 6-pack of beer, I see on the side of it, hey, alcohol by volume, 5.5%. I go, that's not true. Not every one of those is going to be 5.5. I know that for a fact. There's going to be variability. When on the first day of the month, every day, we are a 3-car family. I have a 16-year-old now. And so I take care of the tire pressure of the cars. Guess what? I study the variation. I wonder, why? Why is this tire always a little bit lower than everybody else's? You know why? Because I suspect there's a nail in it somewhere, and I haven't found it yet. But it's my car, so hey. But these things, you study the data, you study the measurements, and you look for patterns, okay? But when I do that, I see these observations, but immediately I think back to what probability distribution. I don't expect you to know all the probability distributions. I don't know all the probability distributions. I have a library of books in my office to help me find the right ones when we get into really difficult situations. But the catch here is, here's what I want you to think about. The diagram is trying to tell you a specific story. The probability distribution hides behind everything. In a statistician's mind, the probability distribution is behind it all. Okay? And the probability distribution will pass its characteristics into the data. Just as a child inherits characteristics from the parent, the data has no choice. It must inherit characteristics from the probability distribution or probability distributions, plural, that generated it. One of the fundamental questions that people ask me all the time, when you do a 2-sample t-test, do you really want to know what you're asking? Do you really want to know? Nobody ever explained it to you this way, I bet. All you're asking is there one probability distribution hiding behind the data? Or is there two? That's the whole question. Because often, when we're giving new drugs, and we put people on placebo, rarely we put people on placebo anymore, but if we put people on the gold standard or standard therapy versus the new drug, if there's only one probability distribution, any difference between the drugs? If there's two probability distributions, then we've got evidence that the drugs are having different impacts. That's the whole issue. So technically, when I look at the data, I'm just asking how many distributions are behind it. That's all. So that's the whole idea, is I take the observational data to make a statistical inference, but in the end of the day, I'm making a statistical inference about what's going on in the probability distribution. Okay? All right, some examples. These are some of my favorite ones. Examples of data. Nature produces hurricanes. Hurricanes typically follow a Poisson distribution. Okay, it's the number of events per year. Every year we get the national forecast for how many hurricanes are going to hit the coast. Right? They're just predicting the rain. I bet you they're just giving you the 10-year average of the past data. That's all they're doing. Okay. Tornadoes, annual rainfall. Annual rainfall, we can pretty much, if we graph it, we start seeing a Bell distribution. We know generally what to expect based upon that. But we see, anytime I look at the data, I look at a data set, I'm looking at the center, I'm looking at the spread, I'm looking at the shape. Why? Those are 3 clues about probability distributions. Every data set has to inherit the center, the spread, and its shape from its probability distribution. Has to. Biology, body temperature, blood pressure, body weight. Be careful here. Let me ask you something, just to kind of tease where we're going. What in Fahrenheit, please? In Fahrenheit, which I know is not a very reasonable measure of temperature. What is body temperature? Speak up. I'm an old man. I'm nearly 50 now. I'll hit 50 pretty soon. What? Speak up.
98.6.
Wrong.
37. There's a distribution.
If I came in here and took everybody's temperature, are you all stuck at 98.6? No. If you got to remember, that's the average body temperature. And you have to keep that in mind. That's just the center of the distribution. We're not all walking around at 98.6. And one of the stories I will tell you over and over is my father has passed away. Really, really good man. But during the last 5 years of his life, I drove people insane, especially nurses, because I would say, what's Dad's body temperature? Oh, he's fine. He's sitting here at 97.9. I go, no, he's not fine. I said, please culture him, because my dad had kidney disease. And they go, why? I said, because throughout my whole adult life, all I've known my father's body temperature hover around is around 97. Dad's thermostat was slightly off. So they were always comparing him to the wrong benchmark or the wrong distribution. We've got to be able to understand distributions. My favorite one, teaching examples, I do this with the Biostats honors class, is M&Ms. M&Ms actually follow a multinomial distribution. And Mars will not reveal what their distribution is. Don't mess with the statistician. We estimate it every semester down to 0.01. No problem. Give me a sample size, we can know what's going on. All right? So those are just ones. But the concept here, as I've already told you, data inherently has variation. If you see variation, then you have a hallmark of probability. If your data is constant, you do not need to call me. I have no benefit to you, okay? If there's no variability, there's nothing for me to bring to the table whatsoever. That variation is being generated by that probability distribution. And it's, okay, let's define our terms. What does he mean by probability distribution? It's just a mathematical model that I think I can describe the tendency of what's happening in your experiment. Okay? And we go through it, and it will help me predict or expect what outcomes and products you should see. Like I said, I already did it. These are the common ones you see. Normal distribution, height, IQ, SF36 are all designed to be normal. Poisson distribution, the count of outcomes in space or time. If you're asking me the number of cultures or number of yeast within a petri dish, you just gave me technically a Poisson distribution, because you've confined, you've restricted. The other teaching example I always give to help people understand Poisson, in fact, I just got one, the number of texts you receive on your phone in a given hour would be Poisson. It may not be a perfect Poisson, but it's close. It's an approximation. The number of bombs, unexploded bombs, let's make it clear that. The number of unexploded bombs per city block, Tokyo, is a Poisson distribution. There are still American bombs in Tokyo that they find. They find 1, 2 every year, unexploded. Same in London, from Germany. Binomial distribution. You get a TB skin test, positive, negative, 2 possible outcomes. Anytime you're studying binomial, 2 possible outcomes. Multinomial, more than 2 outcomes, but still trapped outcomes, yes, no, maybe. Sometimes I will use for my Likert or for my teaching evaluations, if we were going to model it right, which we don't. it would be a multinomial. Okay? When you come to me and bring me the data points, I don't study the individual data points. I do look at them. I look to see if there's anything unusual. Do you have one really crazy value out there? You need to be worried about that, and then I'll come talk to you about it. But never do I study the individual. Like I told you, what I'm going to study is I'm going to study the center, the spread, and the shape. That's the three things I'm going to go after immediately for your data, because they will help me understand what I can match to your data. X bar is always the sample mean. Sample mean, don't let that freak you out. All I'm trying to say is, where is your data? If I had to balance your data on my finger, literally, where could I put my finger in your data set and it would balance and not fall off my finger? It's where the center of it is. Okay, it's a key thing. And then variance, all variance is a measure of dispersion. For as crazy as that formula is, all I'm measuring is where's the center and how much spread is there. Okay, that's all it is. So if I tell you that one data set has a variance of 100 and another data set measuring the same outcomes has a variance of 120, means are comparable, then we know at the end of the day the second data set is noisier. Did you hear the word? Noisier. Means more than likely, if I was going to try to estimate, I'm going to need a bigger sample size. The noisier my data, the more observations I'm going to need to get precision and power. Okay, and I need you to think about this. Get beyond p-values and power. There's a third P. It's called precision. In your approach to science, I need you to do all three of them. Understand what a p-value is, have power if you can, but also think about how precisely can I estimate something. Because it is possible to have high power and low precision and you're not really making a big contribution at all. You're putting out significance, but you're not making precise estimation. Cool facts. Because the data inherits characteristics from the probability distributions, statistics can be used to infer characteristics of the probability distribution, such as where's its mean, what's its spread, how many probability distributions are in there. Under certain assumptions, you will know the probability distribution that governs your statistics that I've summarized from your data. And the mind-blowing fact is they don't match. The data, what generates your data does not have to match the distribution of your statistic. Okay, that's the concept of the central limit theorem that that they poorly explained in your stats classes. Okay? The whole idea being, again, emphasizing this, the probability distribution passes its characteristics into the data. From the data, I get my statistics. From my statistics, I make a judgment about the probability distribution up there, but the one that I'm referring to may not be always the one that I started with. Okay? They don't have to be the same. And now the reason I'll emphasize this is right here. Okay? This is the central limit theorem. Why do we have to teach the central limit theorem in introductory stats? And I just did this lecture yesterday with the honors class, and they were like, why are we even worried about this? Because it teaches the fundamental truth. It says the sample mean calculated on the observations will follow a normal distribution. It tells you a statistic, a descriptive statistic is linked by theory to a specific probability distribution. The second key fact, the first sentence, regardless of where your data came from. I don't care if you started with binomial data. I don't care if you started with Poisson data. I don't care where you started. The central limit theorem states, as long as all the data is coming out of one, I can get to a normal distribution. and make a judgment. It is also telling me that X bar must capture and it must estimate the mean and also the population mean, U, the Greek letter, and that I also have the ability to control the spread of that distribution. This is where power comes from, okay? I have the ability to warp and shrink and collapse distributions to increase my precision by increasing my sample size. Because think about this. Let's just say my standard deviation, this sigma of my data, my underlying data has a standard deviation of 10, okay? If I get a sample size of 100, that means 10 divided by the square root of 100 is 1. So I have made a very precise distribution for the sample mean. But let me ask you this. What if I took it to 225? Now I've got 10 divided by 15, because the square root of 225 is 15. By increasing my sample size, I have dropped the variability of the sampling means distribution down to 0.67. If I take it up to 625, I've dropped it down to 0.4. So I'm increasing the tightness of the distribution. I'm increasing the precision of the distribution. Make sense? Okay, the other thing I did not say at the very beginning is I do like to be talked to. So if you have, and by the way, I have 3 daughters, and my middle one, who is adorable and I love her, she had an incredible speech delay. I mean, literally from like when she started, only her older sister could understand what she was saying. She was the translator for almost 5 years. Now that kid, well, you can understand her and she won't stop talking. She just talks and talks and talks, but she's always, hey Dad, what about this? Hey Dad, question after question after question. So as I go, please, if you've got a question, throw it out. If you need something clarified, throw it out, okay? Should have said that earlier. Any questions at this point? Because we will take a break in about 30 minutes and take a break and then come back and finish up. Any question? Yes, thank you. Oh, it's going to be a long question, so we need a mic. Throw it, Gene, throw it. Toss it. Let's make it a competition.
So when you say the sample mean X bar follow a normal distribution, that's when you have multiple sample means with different sets of X1 to Xn.
No. So that's a great question. So, and if I'm not going to switch on the computer and build a simulation for you, just like I said about Dr. Chaplin, if I have the underlying distribution of total cholesterol for men in the United States, I could say, what's the probability for him? Because the central limit theorem is true, you're going to bring me one sample mean. I can say, what's the probability it should have been that far out, yes or no? You are correct in the way you're interpreting it. It is a long run average. When I teach it in the undergraduate class, I actually say, all right, computer, generate a sample of 100 observations. Calculate me a sample mean. Computer, do it again. Computer, do it again. And what I do is I start out with different distributions. But I say, computer, do this 1,000 times for me, and I show them the histogram. I'll show them a uniform distribution, which is completely a rectangle, just a flat rectangle. But after the experiment, I show them this is how the X bars are behaving, and they see the bell. Then I'll do something like the binomial, where I'll put 25% of the population has a yes, which I'll code as a 1. 75% of the population has a no, which I code as a 0. Computer, 100 people tell me and calculate the sample mean, which is nothing more than a proportion in that example. And you'll see the bell curve appear over 0.25, which is the mean. that you would expect. Okay? And so then I'll take a Poisson, do the same game. Then I'll take crazy distributions like the exponential or the Weibull. The exponential is called the light bulb distribution. It has long tails. How long light bulbs? We use it literally. How long certain mechanical or things will last. Sometimes you get lucky and you get a light bulb that lasts forever. It's rare. And then we'll do a bathtub distribution, which is called the Weibull or a beta distribution. And no matter what I do, as long as I give them a large sample size, I can play that game. There goes the bell over and over. That's all it's telling me. Okay? And based on that, I can predict, and tell you what to expect. So as we go through this, I need you to understand key terms. I'm not worried about you messing up these terms in this discussion with a methodologist. I'm not worried about that. That's not what I worry about. What I worry about is when people present at conference and do these terms get explained. Okay, anytime I do an experiment, I'm going to pretty much force your hand into two situations. I'm going to ask you to help me understand a null hypothesis, and I'm going to ask you to help me understand the alternative hypothesis. Okay? I'm going to give you a hint right now. No matter what, your research hypothesis will be the alternative. It has to be. Okay, we have to set it up that way. Okay? Now, let me just make it very clear to you really quick, okay? We all understand hypothesis testing. We've all understood it for years. You just didn't get it explained to you in the correct approach. In a jury trial, what's the assumption about the person on trial? What is assumed to be true? More than that. It is actually a declaration of innocent. The person is innocent. That is the assumption. That is the assumption in the trial, period. That is the null hypothesis of all jury trials. Person is innocent, right? What's the alternative? What are you trying? Does a prosecutor bring anybody into a trial with the hope of the prosecutor proving their innocence? In fact, it can't be done. We are forbidden by the Constitution. It's a fundamental concept of the Constitution. No one is ever going to be brought in to prove their innocence. That has to be assumed to be true. Okay? So what's the alternative? What's the prosecutor going for? Guilty. You're the prosecutor. You're the prosecutor in every experiment you do. You are trying to present a body of evidence that will indicate the alternative is more likely true than the null. That's what you're doing. Exactly. Okay? It's always the research hypothesis. Now, let me ask you something one more time. Another thing, okay? This is where it gets a little tricky. When a jury is called to evaluate the evidence, they are called to evaluate the evidence under what condition? Think for a minute. That's the alpha. We're going to get to an alpha in just a minute. What did you say again one more time?
Beyond a shadow of a reasonable doubt.
All right, I'm going to pick on you a little bit, but it's only out of kindness, okay? I'll clean that up in just a minute and give you a piece of trivia that you'll never forget. Okay, that's the type 1 error rate. That's a great approach to type 1 error. You must evaluate the evidence under the belief the person is what? Innocent. So in other words, all the data is when you look at all your evidence, you're literally asking yourself, how compatible is the evidence to this belief I must hold? Okay, person was murdered downtown Friday night. Dr. Redden's cell phone can clearly be traced to downtown. And he was near that block. But of course, he was having dinner with his family of 5. They went to see a play at BJCC, and at no time did Dr. Redden ever leave the company of his family. Is the data compatible with the belief that I'm innocent? Yes. Is it really compatible? Yes. That's it. Done. There's your p-value. P-value would be high. High p-value. P-value very, very probable. That data matches my belief of innocent. Now, Dr. Redden was also on the block. Dr. Redden's blood is on the victim. The victim's blood is on Dr. Redden's clothing. Dr. Redden's DNA is on the gun that has been matched to the bullet holes and the bullets that were found in the victim's body. Now, how compatible is that evidence with the belief I am innocent? That does not match. The probability of that preponderance of evidence with that belief is low. Probability low. Now back to you, okay? Your name?
Elizabeth.
Elizabeth. The jury is called to make a line in the sand. It is what is called a type 1 error. A type 1 error rate. What is the worst thing we can do in the American judicial system? Send an innocent person to fry. We don't fry them anymore. We would send an innocent person to prison. But I will bring up the death penalty in just a minute. Okay? A type 1 error is accidentally rejecting the null hypothesis, a person's innocence, and sending them to prison and convicting them, right? We have to have that threshold beyond which the evidence carries us over. We can make an incorrect decision, but we have to put a threshold down. And that threshold is evidence beyond a reasonable doubt. No shadow. That got introduced into the shadow of a reasonable doubt got introduced into the American vocabulary by a TV show called Perry Mason. I'm serious. The actual criteria is beyond a reasonable doubt. It's just a line. Does everybody on a jury have that exact same value? No, but in science we've tried to force it with the 0.05. Bad idea. That was a bad idea. But when we say 0.05, our significance level is 0.05. That's our evidence beyond a reasonable doubt. That's the level. We're asking for anything that would have occurred 5% of the time or less. That's going to help us decide to jump from the null to the alternative. That's it. Okay? But please understand the probability type 1 is given, it is true. The p-value, the probability of observing the data or the test statistic given the null hypothesis is true. Given the person is innocent. Okay, it's not the other way around. It is, okay, we're going to play this game in a little bit called true false. Then I'll give you the 5 ways people butcher the p-value and beg you never to say these, okay? Never. All right? Power, when we say somebody has a powerful case and we're doing a jury trial, the prosecution has a powerful case. What does it mean? It means more than likely they've got very convincing evidence and they're very likely to be able to reject and get the jury to believe the person is guilty when the person is indeed guilty. Okay? I want to ask you one more thing. And this is a key thing that will save you if you will remember it. At the end of a trial, bailiff comes in, the jury comes back in, foreperson stands up, hands a piece of paper to the bailiff walks to the judge opens it, reads it, judge hands it back to the bailiff, back to the foreperson, whoever they may be, they stand up and they read one of two outcomes. What are those two outcomes? What are the two declarations?
Guilty, not guilty.
Perfect. Guilty and not guilty. Exactly right. Why don't they say innocent?
There's still a chance.
You can't prove something you assumed. Can't do it. Remember, you conducted the whole trial assuming the person was innocent. So all you can say is guilty or not guilty. So when you fail to reject, please don't get up to a podium and act as if you proved the null was true. All you can say is, I can't reject. I did not have evidence to reject this statement. That's all you can say. Key thing here, I clarify this with Pearson correlation. I think I also got somebody online that has a question, or we got a question right here. Question right here. Pearson correlation. Be careful when you talk about it, because correlation is a measure of association. But be careful. If you say is linear, it's a linear association. Can I put a line through my data? The first question is a line reasonable? If not, then we have to come up with another measure of association. Hint, always look at your data. Look at graphs. Graphs are more important. Record this. Graphs are more important than the p-value. Yes?
Okay. I hesitate, but I want to know, David, why you don't have type 2 error listed under
Because most people, all right, the question is, there are two types of errors, and that is true. Every time you make a decision in your life, you have the potential to make not one, but two errors. One, you got to make a choice. You choose A, but you should have chose B. You chose B, but you really should have chose A. That's life. You're always going to make those mistakes. You've got the chance of that. We control type 2 in the design. Okay, we control the type 2, but we set type 1. We, as a team, a group of team scientists working together, will decide what is the appropriate level. We are not going to act as if 0.05 was chiseled in the stone that came off of Mount Sinai. Okay, it is not. I'll tell you why it should not be that way. It was never intended to be that way. It's just because we got lazy in writing our textbooks. Serious. I'm being as serious as I can be. But I control type 2 by my sample size. And people don't really want me to talk about type 2. They want me to talk about power. And power is always 1 minus type 2. So if I'm talking about power, I'm simultaneously talking about how I've controlled the type 2 error. Okay? And I think next week we go into power. I'm going to demystify it. I'm serious. I'm going to make certain that you literally visually see power calculations. No, not some mysterious incantation that comes out of some like warlock's spell book. Show me a graph so I can understand what you are talking about, sir. You'll see those graphs. Okay? Go.
So,
I think it'd be wise to pass the mic. Gene, toss it. Let's see if people can catch.
I'm not a good catcher.
Okay.
So often people discuss, when you have a continuous variable, and some people say the sample size is big enough that you can use t-test instead of rank sum. And when they say that, n is greater than 30, is that because they don't understand the central limit theorem, or is that concept coming from another theory?
No, that's a great question. So let's back up to the central limit theorem. I'm not going to back up to the slide, but the question, what it's boiling down to is the idea of what is a sufficient sample size for the central limit theorem to be considered invoked. And again, the textbooks get lazy. They most of the time will throw out 30. It all depends on the underlying nature of your data. If it's already symmetric, I can get a pretty good approximation on a sample size all the way down to 12 or 15. If I know the underlying distribution started out as symmetric, it goes really fast. However, generally the rule is when we start getting into the 30s and into the 50s, no matter what the underlying distribution was, central limit theorem is kicking in fast. So that's it. Typically, you brought up the idea of when would we use a parametric, such as a t-test, versus a non-parametric, which is kind of like a Wilcoxon range sum. I will choose on that, and I would talk to my investigators about this. If I'm not comfortable having enough evidence, either through graphs or through sample size, for me to believe I can invoke the central limit theorem, and you should probably talk to a statistician or a methodologist about this, that's when I fall back to the non-parametrics, okay? But it's always not, I never just make it a rule of sample size. I will always go to graphs. Again, take home message, what a p-value is, this guy, and the other thing is look at your data. Look at your data. Get with the methodologist, look at the shape of your data, look at the assumptions of the data. Okay, now I'm going to get into this. Let's see, let me look real quick. I'm doing great. Not really. I'm going to explain this. I'm going to break us for 7 minutes exactly. I like 7. 7 minutes. That way you can get coffee, take a break, get more nutrition. And I'm going to go through these. And notice I throw myself under the bus. Most teachers, including me, but it's good. We teach it. It has its role, but unfortunately, everybody leaves the end of the semester thinking, this is the only thing I've got to do. It's not true. There's more to it than just hypothesis testing. But I want to point out that, again, this is nothing more than a quantification of the scientific method you learned in 6th grade. Do you remember, like, your 6th grade science class, they were talking about state your hypothesis, collect your data, summarize your data, draw a conclusion? Guess what? That's what I do for a living. But I just do it with probability distributions. I have to help you write your specific aims, because your specific aims help me understand what the null and the alternative is. Before I came in this morning, I got up at 5 a.m. and did a power calculation for somebody. You know where I started? Group down in Auburn. They sent me their specific aims page. From there, I knew we're testing a correlation, whether it's 0 or it's not 0. They asked, what's your sample? Well, how much sample size do I need? They didn't give me all the information, so I gave them a range. Talk about it on Friday morning, send it to them. All I do, state the null, calculate the appropriate test statistic. Methodologist here, Monday, Wednesday, over in Lister Hill on Mondays, here on Wednesday. Office hours available to sit down with you to help you design it and pick the appropriate test and conduct the appropriate test for you. But at the end of the day, we're all driving toward a p-value, because this is, if you remember just one thing, all right, so I'm asking you to remember a lot of things. Calculate a p-value and compare to the type 1 error rate. I don't read if p-value less than or equal to the type 1 error rate. I don't read it that way. I read it if evidence beyond reasonable doubt. Substitute the word evidence for p-value, because the p-value is your evidence. Less than or equal to is beyond. Type 1 error rate is reasonable doubt. That is the exact interpretation of what we're trying to do. Because the probability is so low, you have observed an outcome that is not compatible, should not have been observed. If the null hypothesis is true, we are beyond a reasonable doubt. We move to the alternative. That's it. But every p-value is calculated as the probability of observing this under the belief the null is true. Under the belief the null is true. Just like you do in a jury trial. All right, break. Then I'm going to give you the history and I'm going to use foul language. Something to look forward to.
So I was working on a dice and I have a presentation and it was distribution. It was because so I said that person said, well, because you have so that's the
No, I would not do that because the t distribution still assumes. This t distribution still assumes normality. To get to the t, you have to assume normality.
So that the person's
It is a misunderstanding of the central theorem. Yes, it is. It's a misunderstanding of the t distribution also. The t distribution assumes you have a standard normal divided by the square root of a chi-square, divided by its degrees of freedom. Both those assumptions require your underlying data to have been normal. Now, let me go a little bit further. The t-test can be robust, but I would have followed along with you. I would have just said, let's do a non-parametric. How many observations did you have? Just do a non-parametric. Just do a non-parametric. Okay. That was a good question. Sure.
I don't know if I'm understanding this correctly, the p-value and the time. So I understand the p-value is more of a probability of observing the data, and the time rate is probability of rejecting the hypothesis. But how do you actually calculate time rate?
You don't. You assume it.
Oh, you assume
You never calculate it. You do not calculate a type 1. Though, and we're going to get into that. You calculate the p-value. The thing about on a jury trial, you have to decide what is beyond a reasonable doubt. We pick, and you pick a level, and part of my job is to help you guide you.
What we set the number at.
Yeah.
Can you explain this slide one more time?
Sure.
I think I didn't quite get it.
Okay. Okay. So going back to there was a great question about, you're talking about the sampling distribution of X bar.
Right.
Okay. So let me go back to this idea. Let's talk about TB skin test. Okay. Because one of my first projects, we did a lot of studying with the Alabama Department of Public Health about truth. About 1 out of every 10 individuals in the state of Alabama is going to, if I give you that skin test, boom, you're going to react. Doesn't mean you got to do it.
I have to argue with them every time for that.
I know. But here's the kicker. If I went out and I gathered 100 individuals and I estimated the number of individuals or counted the number of individuals that I got in my sample that were skin test positive. Suppose I got 10. That gives me a proportion, a mean, literally a sample mean of 0.1.
Right.
I do it again. I get a sample mean this time of 0.2. I get another, do it again. Sometimes I'll get 8, 0.8, 0.08. If you keep doing it over and over and over, your underlying data is not normally distributed. Your underlying data is binomial.
Right.
It's either yes or no. But if I start calculating the sample mean, and I look how that sample mean behaves, There it is.
And that's the central limit.
That's the central limit
Okay,
theorem.
all right, I didn't put 2 and 2 together.
That's fine,
but I think
that's
I
fine.
get the concept. Thank you.
Fine.
Okay. Feel better.
Hello. See you. Nice to see you again. I'm fine. I'm gonna steal a scone. Oh, somebody's already gone through all the scones. Darn it.
That's good.
I'm just playing. There's still scones here. Yeah, I'm just playing.
I had the NPAs. I studied with the senior school when I was at NYU. The first year, and they split us up. And the public administration, government.
I see Meredith's got her business cards.
Oh, it's the holidays when everybody does. Everybody wants to get in. So, I was in the business school economics. You know what?
I usually like.
No, I was just talking about.
I didn't. I'm sure they heard my voice drop and then ran away. Don't you agree, Jamie? They probably heard my voice and just dropped and ran in fear. How are you?
Pretty good. How are you?
I'm lecturing. I told you I'd come by and see you. Okay. You worry about me, I worry about you. I think you've underestimated just how jaded and how mean I am.
I have a great understanding.
And that didn't surprise me because she came in and I joked with her. I said, "You're riding today." She goes, "How do you know?" I said, "You wore your running shoes." And she always tells me, "I ride so much better when I'm wearing my running shoes." No, but I need to go home to write, but I haven't. I'll stay up tonight and write and stay at home in the morning and write and finish mine. All right. Yes. That'd be fine. He'd be very good. Yeah. But Dustin's already in the. I would definitely bring in Dustin. He's very good. I would also bring in his wife, Leanne. Dustin and Leanne were both very, very good. Mm-hmm. Okay, 7 minutes are up, according to my watch. But everybody can come back in slowly. It's all right. So now I'm going to give you the truth of why people can't understand. Why, if you go and you try to, and the other thing that's odd in textbooks is power. Everybody really wants to design. The whole purpose of statistics is to help you design experiments, right? Help you design experiments, help you to be able to quantify the outcomes and draw, big word, inference about what's going on. Make a decision. But I have to tell you something. When you look at a stats textbook and you say to yourself, dang, that's confusing, there's a reason. Okay? Here's the reason nobody will tell you. All right? We teach null hypothesis statistical testing, this 4-step dance. State your hypotheses, collect your data, calculate a p-value, draw a conclusion. That's the way we go. Compare it to alpha or type 1 error. Well, go back to the father of statistics, the one that we talk about, R.A. Fisher. He proposed the p-value. When he was doing his experiments, 1910, 1920s, when all this was going on, early 1930s, he simply said, set up a null hypothesis, calculate a p-value for that hypothesis, report the p-value. Okay, that's all he did. That's all he did. That was his approach. What was he doing? By allowing you to see just showing you all of it and handing you the p-value, he was trusting you to be the scientific jury. He was allowing every member reading or every person reading that article to be allowed to define for themselves, just like a jury does, what is beyond a reasonable doubt. Okay? Now, as is very common in academia, we have wars. There was a competing group. I have 3 daughters. I love them deeply. I joked with my wife that if we ever had a son, I was going to name him Egon.
Oh.
Yep, that's what she said too. She said, over my dead body. But null hypothesis testing did not come from R.A. Fisher, who was the father. It didn't come from Neyman and Pearson either. They came up with this idea. Set up a null and alternative hypothesis. They came up with, we've got to have 2. They say, and you will pick a type 1 error rate. Using a type 1 error rate, you would draw a graph and take parts of that graph and say, if you're inside these regions, reject the null hypothesis and choose the alternative. It was called the rejection region approach. Otherwise, if you did not get that, you would conclude the null hypothesis. Need to tell you, Fisher and Pearson did not get along. 2 stories, more than just for the fun of it. Pearson goes to present at an international conference. I mean, they hated each other. It's pretty much documented in some, if you really have insomnia, read the history of statistics. Yeah. Pearson's up talking at the podium. This is a conference. It's in Paris, delivering all of his results in French. There's Fisher standing in the back of the room, arms folded. Pearson starts to sweat, literally thinking that he's about to get chewed in public and get into a fierce debate again with Fisher. Pearson sits down. Fisher walks out of the room, and the other guy that's presenting with him leans over and says, calm down. Fisher doesn't speak French. They didn't get along with each other. Neyman and Pearson decided that they needed to leave. They were all at Oxford together. They figured they needed a little bit of distance. They decided to go to Stanford. Was that enough distance? They literally, it was a hatred. A hatred. If Pearson was the editor of a journal, Fisher never published ever in that journal. And for every journal that Fisher was an editor for, guess what? You don't find a paper from Pearson or Neyman in those journals ever. It was very much. And if they were alive today, they would kill every one of us. You know why? Because we took their very competing theories And instead of deciding which one was right, smashed them together, wadded them all up, and put them in one textbook together and combined them all. That's why it's so confusing. That's why it's so confusing, because if you read Fisher's articles, he never talks about an alternative hypothesis, and he doesn't talk about type 1 error rate, and Neyman and Pearson never talk about a p-value, ever, because they were in different camps. But what we've done is we've smashed it all together in one textbook, and most textbooks have gone away from teaching rejection regions. I still teach rejection region in every class I teach, because if you can draw a rejection region, you can draw a power curve. But with that, if you're just looking at p-values, power becomes very, very confusing. Okay? We're going to cover that next week. Where did the 0.05 come from? This is no joke. 0.05 came from the fact that people kept hammering Fisher. What's beyond a reasonable doubt for you, Dr. Fisher? What's a reasonable doubt for you, sir? They asked him over and over and over. Are y'all ready for this? In a footnote in a paper, or it was a footnote in a book, where he states, for some, 1 out of 100 will be sufficient. For others, 10 out of 100 will be sufficient. But for me, in general, 5 out of 100 is sufficient. And now all of us use 0.05. It has been a disaster with genetics, especially with the proliferation of data from genome-wide association studies. You can't use 0.05. You're flooding the literature with way too many false hits. You're doing way too many tests. So you just have to be, it's really one of the things that we've got to do in the next 10 years in statistics is come back and figure out how do we address a correct type 1 error for different studies. Okay, so here's my swearing. What is null hypothesis statistical testing? It's a bastardized version of 2 very different approaches. It's literally, we took 2 warring camps. We'll fix this. They're dead. Who cares? And we completely, and we hide it all in the textbooks. You don't know that. But now you do. Does this mean it's useless? No, it's not useless, ladies and gentlemen. It's not useless, but it is it's tunnel visioned. Everybody just hones in on that p-value because you can, boom, boom, judgment, judgment, judgment. Now we can't go. You need not only the p-value, you need graphs, you need the whole all of it, okay? I will not agree. I can give you articles that have told, there are journals out there that now forbid the use of p-values. I'm not joking. That will not publish if you are trying to publish it with a p-value. I think that's an overreaction. It's not that the method is wrong. It's that we've done a poor job of teaching the method, explaining the method, and explaining its limitations. Okay? Don't overinterpret significance. I mean, bottom line, one of my teaching examples is I can give you 2 graphs that are in 2 groups. And I can tell you, give you 2 box plots, and those distributions are clearly nowhere near each other. And then I keep moving them away. Are you convinced now? And everybody's going, yeah. And I will show you, and I can prove to you mathematically, no matter how far apart I pull them, p-value will never get below 0.10 because of a limitation of the design. So you've got to know these types of things. I would say publish the graph. Don't worry about the p-value. All right? You do not always have to use a type 1 error rate, though this seems to be the convention. It should not be. Okay, and I'll tell you why. I conducted a multi-million-dollar clinical trial one time. Not me per se, I was just the statistician on it. I designed it. And the PI started to cry when I said the p-value was 0.052. I'm not joking. Again, that's a misunderstanding of what the method's supposed to do. Are you all of a sudden, oh yeah, there's no evidence there whatsoever that behavior is just as effective as drug? 0.052, do you think 0.052 is really that much more different than 0.049? Okay, no, it's not. Also, the other thing is to remember that you don't always have to compare back to zero. We teach it, and we always set the null hypothesis to zero in most trials. We don't have to do that. We could set it to another value, and I need you to be able to define for me what that value should be based upon your clinical expertise. Okay? We'll get into that more. And the other thing, please resist misinterpreting the p-value as something it's not. Okay? And that's when we get into our new game. Let us play true false. Okay, don't look ahead. Don't cheat on me. A researcher reports that the p-value from his or her hypothesis test is 0.01. Based on this information, the researcher has absolutely disproved the null hypothesis. False. That's an easy one. If you want a proof, get the math department, not the stats department. Okay? All I can do is give you evidence. Okay? That's a false statement. But I have had people come up plenty of times, and I've been at conferences where people have said, well, my p-value is 0.0001, and that proves the null hypothesis is not true. Nope, does not prove it. Nope, we'll never accept that statement. Researcher just saying p-value, the probability the null hypothesis is true is 0.01. I've had this one. Is that true? No. Hence, hint, if you want a proof, get the math department. If you want truth, find the philosophy department. Okay? I cannot give you truth. I can measure evidence. Evidence can be misinterpreted, and evidence can be used to draw wrong conclusions and correct conclusions. And I am using the laws of probability to try to control the rate at which you make those. Okay? So again, and I've had it. I've found journal articles that have published that have stated p-value is 0.01, therefore the probability of the null hypothesis is true is 0.01. I'm like beating my head on the table. It's not true.
What's the best way to change that to make it true then?
So I take a red marker and just take it completely out because it's completely false. I'm going to give you the correct one in just a minute. We will end with the truth. Literally the correct one. Based on this, the researcher has absolutely proved the research hypothesis. No, these are all classic overinterpretations. Step way, way back from these statements. False. Now we're going to get closer. Based on this information, because all of them start with the same assumption, 0.01, 0.01. Based on this information, assuming the researcher rejects the null hypothesis, there is a 0.01 probability he or she is making the wrong decision. This is trickier now. True or false? Easy ones are over.
False.
Thank you. How'd you know?
Because it's not a probability of the decision. It's a probability of the data fitting.
Bingo. Now you see, exactly. The p-values, the probability of observing the data under a belief the null hypothesis is true. If you will anchor to that, you will stay away from misinterpretations. Do I have a psychologist in the room? By the way, I'm married to a psychologist, so it's nothing personal. Do I have a psychologist in the room? I do not. Do I have a psychologist online? If you're offended by this statement, it's nothing personal. This is a classic interpretation in psychology journals. they substitute the idea of p-value and type 1 error rate, and they swap them out. And that's not correct either. It is true that you could continue to lower your alpha to this level and continue to reject, but that is not the probability of a wrong decision. Okay? How about this one? Same p-value, 0.01. Based on this information, the probability that the null hypothesis is true given the data is 0.01. True or false? All right, I've got one very confident person shaking their head at me as a no. How about the rest of my crowd? All in favor of false. Oh, I love people doing this. I'm doing this. All in favor of true. All in favor of not playing my game. Okay, so right now I have a response rate of about 45%. And that 45% has voted that this is a false statement. 55% of my sample is refusing to cast a vote. So therefore, this statement is false. Why is this statement false? I've reversed the conditions. Remember what I told you? The p-value is the probability of the data. Remember, p-value is the probability of the data, or data more extreme, under the belief. Given the belief the person is innocent, or given the null hypothesis. I flip the two. The probability that the null hypothesis is true, given the data. No, that's the reverse. This is what people want to say. This is what they desperately want to say. And this is what people have put in the literature, and it is wrong. People will interpret it this way. This is what is called Bayesian statistics. It requires a ton of assumptions to get to that statement. I do believe there's a place for Bayesian statistics. I really do. However, you've got to put those assumptions on the table and show the sensitivity of what you're doing, okay? One of the things I would hope to do in the next 20 years of my career is to get more and use more Bayesian statistics and get it used more often. But because at this point in my career, I see the problems. I would like to be part of the solution, not part of the problem. What about this one? Based on this information, the probability of observing the data or data more extreme given the null hypothesis is 0.01. There's a 1% chance that I should have gotten these outcomes if the null hypothesis is true. Is that correct? All in favor of saying false, raise your hand. All in favor of saying that's finally the true statement after all these games. Is this the truth? This is the truth. This is the way to interpret it. And if you will go find the articles that I put out clinically, not my methods papers, but what I do clinically, I make certain that sentence appears. Even if the editors try to take something else, say shorten the paper, fine, I'll take away something else. I'll take out a description of my normal probability plots, but I'm going to make certain the interpretation of the p-value is correct, okay? There was under the assumption that we made to evaluate the data, there was a 1% chance of getting data like this or data more extreme. Okay?
What do you mean by data more extreme?
All right, well, that's great because I'm going to show you that next week when we do power, when I draw the curves, okay, when I calculate a p-value, probability by the distributions is an area underneath a curve. So to get the area, I have to talk about going out into the tail. That's where my phrase more extreme comes from. Okay? All right. There you go. False, 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 false. Bayesian interpretation. True. Okay? But just please, if you, got 30, I'm going to try to get us out of here 15 minutes early. But listen to me. I'm not asking you to be the cop. I don't like gotchas. I don't want you to be doing that to your colleagues. That's not the point. But in your research, in your explanations, do your best to keep it anchored on what it really is. The reason it's going all wrong is because we're sloppy in our explanation. We're sometimes sloppy in our technique. But if we can just do it better, it will be all right. So here's an example. Let me walk you through it. This is the classic one. And I'm going to, again, small sample size. I'm going to make some assumptions about normality here. Basic example. Let's assume we wish to test whether a difference exists between total cholesterol levels between men and women. We collect small random sample, 10 men, 12 women. We'll use my type 1 error rate. Notice I specified it up front. I picked that. You picked that. Okay? Put it down up front, 0.05. We'll assume normality so I can do a t-test. You end up getting the following data. You'll end up with a sample mean. You'll end up with a sample mean for men, sample mean for women. You'll end up with a sample variance for men, sample variance for women. We'll pool all that information down to get a t-distribution. And the question comes down, okay? I'm literally doing a test, mu1 equal to mu2. If those two population means are the same, I have one distribution governing my data. There's no difference between the probability distribution for men and women. If the alternative is true, I have two probability distributions. One that's distinct for men, one that's distinct for women. That's all I'm saying. Based on the data and my assumptions, I get a t-statistic of 2.69. That's my summary of all my information. I distill that down to a p-value of 0.0142. Then I come in and say, well, evidence beyond reasonable doubt. So I reject the null. My question for you is, how would you write that up? How would you write that? What would you say? If you were going to try to put that in a journal, what would you say? How do you avoid overinterpreting it? That's why I gave you the following slide, kind of like a template. Okay? I would just simply say there's sufficient evidence at alpha equal to 0.05 to reject the null hypothesis and conclude that the mean cholesterol levels differ between men and women. That's it. I have said there is evidence. There is sufficient evidence. That's what I'm doing here. I'm judging my evidence. The evidence at this level is sufficient to conclude there are two probability distributions. Okay? Straightforward. That's pretty much what I'm doing here is I'm revealing that I am using both ideas from Fisher and Neyman Pearson. The first one is exactly what Neyman Pearson would have written. The second one, the probability of observing this data or data more extreme, assuming the null hypothesis is true, or assuming there is no difference between men and women. You probably would have been cleaner to say assuming no difference between men and women to be true is 0.01. I'm giving you both those interpretations. And that to me is the safest way to go. All right? The rejection region approach, this is what Neyman and Pearson would have done. I want to give you, and so back to your really great question of what do I mean by more extreme or not? It's this area out into the tails. Do you see where I dropped the black marks? If we were just doing the Neyman-Pearson approach, Neyman would have said put 0.025, half my alpha, 0.05 divided by 2, put half into each tail, and find cut marks to find that region. If you get anything that falls within that region, it's called a rejection region for a reason. What do? You reject. And this is just an illustration that my test statistic is 2.65. It falls right up here. Therefore, if I used Pearson's approach, I would draw the same conclusion. That's the thing that baffles people. Why do they hate each other? Both their methods always agree. They always agree. If you go with Neyman Pearson and use his rules, you're going to get the same result if you went with an alpha and used the p-value that that Fisher gave you. So, I personally kind of like the rejection region approach. I'm old school. We're going to get into power more next week. But the idea of power, again, I'll be very honest with you. I don't think people keep me around to actually do the analyses. People keep me around because I can help them understand the idea of power and how to go about building it. Okay, Dr. Redden, I've got to do this experiment. We're going to put this grant in for the federal to get this funded, but they want to know, do I have a good chance of finding a difference if it exists? That's what power is. We teach, the answer is useful to calculating power and to seeing power. Suppose I wanted to know what's the probability if the truth is that there actually is a 5-unit difference between them. Do I have a good chance? What if the alternative is true? So let's go back to this, okay? Because I just got a baffling look. Let's back up. If I ever go to calculate power, which I will all day long, what I have to do is power only makes sense if the alternative is true. Therefore, mu1 cannot equal to mu2. Cannot. We have to imagine a scenario. Pick me a mu1. Pick me a mu2. Please make certain that they're not equal. And then let's talk about if the alternative is true. What's the probability I would be able to reject and declare? I can find that difference. Okay? And this is the idea. This is really where I spend the vast majority of my time working with all investigators. Not young, I mean all investigators. You will be doing this for a lot of your career. What's a clinically relevant difference? You'll hear me ask you that over and over. What's clinically relevant? Okay, let's just hypothesize. It's 5. Okay, then what happens is there's the distribution. This is a preview for next week. There's a distribution that is that's going on for the null. But under the alternative, if you imagine that there's a 5-unit difference, there is the alternative distribution that has been defined. Do you see this line right here? Okay, for you to understand what power is all of the area underneath the blue curve that is falling above my rejection region. So stop and imagine for 1 minute, okay? Suppose I didn't say a 5-unit difference. Suppose I used a 10-unit difference. That blue distribution is going to be shoved. Literally, imagine it. I'm shoving it over to the right. More and more of that distribution is falling above the cut point. So power is going up. So when I hypothesize bigger differences, power will be high. The other trick I could do is force the distribution to collapse, make it far more tighter. How do I do that? Sample size. I throw my sample size higher, and that'll force my curves to collapse in. Okay, so that's what really power is. And you should ask to see these types of graphs. And can you show me a graph if I assume this? And can you show me a graph if I assume that? And then it's just literally shading. Just shade the region that fell above the rejection region. So, okay. So here's the truth. Modern hypothesis testing, you're left with the probability of observed data more extreme, given the null hypothesis is true. There is no other way. You've got to stay there. That's it. You've got to stay there. That's all it is. My best advice to you is not to get tunnel vision regarding p-values. There is so much more to research than p-values. Give them graphs of their data. Can I make a joke to you? When the atom bomb exploded, did they need the statistician? Did they? No. There are certain physical experiments that go well beyond needing quantification. Graphs are helpful. Images are helpful. P-value, build the whole landscape of what's going on. Okay? When a p-value is appropriate, use it. But ask yourself 1,000 times and talk to the methodologist, what things other than the p-value should I be presenting to convince them that there are multiple distributions? Okay? To help buttress the case that the alternative is, we believe the alternative hypothesis is true. Okay? If you fail to reject, resist the belief you have evidence for the null. You don't. All evidence was collected for demonstrating the alternative. People hate statisticians because we like the little riddle of absence of evidence is not evidence of absence. Think about that. Just because you fail to have evidence doesn't mean you have evidence that there's an absence. Okay? We actually sell that t-shirt at conference. It's kind of sad. Simply say, we do not have sufficient evidence. It's the statement. We do not have sufficient evidence. It's the same thing. We don't say they're innocent, because we don't. We can't. We do not have evidence to declare them guilty. And that's the end of the trial. Use the whole toolbox, and I'll try to bring you next week when I'm up again more fun articles if you want to read them. Mindless statistics, if you want to go find that, that's an interesting read. My favorite one is by Jacob Cohen. Jacob Cohen, who is the guy who did massive books on power calculations. I loved it. He said he sent an article in that said the Earth is round. We have a p-value demonstrating that it's at 0.05. We have a 0.05 level. We have proven it. Yeah, thanks, Jacob. And then we got these other ones that if you want to go study, they're all very good. And I did it with 4 minutes to spare.
Okay.
All right, next week we do power. Okay, and we'll talk about correlation also then. You have any closing questions? No? Then enjoy some more snacks and more coffee, and I'll see you next week.
Thank you.
Mm-hmm.
I just graduated from that. So you won't be here right before the split. Biostatistics department. Eureka was mine.
Oh, wow.
Because I wanted, and I paid student and we had to have a minor. So I wanted biostats, but then he had to give me the whole history of what happened to the department. So I had to come to UAB and do my minor and end up doing it in general.
Well,
Completely.
it's interesting because there's also, I firmly believe in a fallen world. Because what's ironic is, yes, there have been wars at Tuscaloosa. There have been wars here that I've tried to put to bed for the past 10 years. Still fighting that. So. Dr. Marcus, you have a question?
Yes, okay, so, you might want to know where this this might be something you're gonna go over next week or.
But I can.
Okay. And what the degree is.
Degree